Okay, any other biomedical devices, organs? The next item is nanotechnology.
Okay, so the basic idea is that we want medical nanodevices, and if we want medical nanodevices in 20 years' time, then we have to plan and execute a plan to have them, or 20 years will come and we won't have medical nanodevices, which would probably be disadvantageous for a number of reasons. The primary requirement in the near term is to develop molecular mechanosynthetic devices, in other words, molecular tools. The molecular tools are the kind of molecular tools that would allow you to build molecular structures. If you look at scanning probe microscopy today, you find that there is research and there are experimental demonstrations of arranging atoms on a surface. In the next few years, we have to move off of the surface and into 3 dimensions so that you can build three-dimensional structures with small numbers of atoms in them. In order to do that, what we need is a lot of analysis of what sort of structures you could build, what sort of tools you would use to build them, and some kind of scanning probe microscope-like device that would be able to carry out those particular motions. The particular thing that needs primarily to be done is extensive computational modeling, because if you are going to build these things experimentally, it would be nice to have some degree of confidence before you spend a lot of money building them that in fact they will work and you will be able to carry out the various operations. This can be done effectively today because computational power has been dropping and because computational chemistry software is now available, which will let you look at, analyze, and model the molecular reactions, the tools, and the products that they will build. It looks as though in a period of 10 years, we could go from where we are today, develop the computational techniques, and develop the hardware that would let you do that for a price tag of about $30 million. We're looking at maybe $1 million in the first 2 years, and then you double every 2 years. So you double from 1 to 2 to 4 to 8 to 16, and that gets you something like a decade. And then you're looking at a total expenditure about $30 million. And once we have that, once we have the ability to build a small number of molecular devices, although expensively, we can then use that to bootstrap into the nanofactory over the course of the next decade. And from there, we can build the medical nanodevices, which are the devices we all want. Oh, and by the way, once you build a nanofactory, you will also be in a position to make sums of money that are obscene. So that is another benefit for those who are looking for an additional motivation to pursue this particular technological development pathway. So,
any additional comments on nanotechnology?
Diagnostic devices. Would you like to maybe comment on designing continuous monitoring biomedical devices using current nanotechnology?
Current nanotechnology. I don't know. Do you want to comment on current nanotechnology? We'll pass on that one, yes.
Passing on that. Okay, I think of cryonics as the ultimate backstop for everything that we do. So I propose that rather than have Ralph continue, maybe we'll interrupt Ralph with a little comment from Greg Fay about cryonics. Give him the microphone. Surrender it, Ralph. There you go. You'll get it back, don't worry.
All right. Unprepared as I am for public speaking about this subject. Yeah, untested. Yeah, I don't normally talk about cryonics in public. This is a friendly group, so I guess I can let my hair down a little bit. I think basically cryonics is going to work provided that it is done correctly. And as far as what's needed in that regard, it's a difficult problem, but money could be helpful in dealing with that by finding better people to help carry out the procedures and implementing procedures. I specialize obviously in the cryopreservation side of things, but the part of cryonics that Ralph skipped over, and I think that was a wise and strategic choice, is what happens between the time that the team arrives at your bedside and the time that they start pumping you full of cryoprotectants back at the lab. A lot of time can elapse, and what we've discovered at 21st Century Medicine in other experiments is that, at least in animal models, even a nice, fresh, healthy animal is badly damaged during the period of transport. It's a more serious problem than the cryopreservation itself at this point, because we can cryopreserve brains and the ultrastructure is perfect, and we can warm them up even, and the ultrastructure is perfect, and we can add and remove the cryoprotectants and the ultrastructure is perfect. And we can even, actually, on one occasion, we got nice electrical activity of a brain back after loading and unloading the cryoprotectant. So we're pretty good. We're still working on it, but we have a ways to go. We're pretty good on the cryo side. So I can present a really slick thing to Ralph to work on 100 years from now, and he's going to have a real good time, with that inference process and reconstruction process, provided that the patient got to the cryo stage in one piece, and that's what needs a little bit more work and clinical study. So in terms of cryonics, I think you could do a lot for cryonics, both technically and in terms of its practicality, by focusing on things that give some feedback, as to how good a job you're doing, and use the feedback to present to people in positions of authority to indicate to them that the whole idea is not completely nuts. Because if you could get the medical establishment to buy in the cryonics, and you could get the procedure started at your local hospital, it's going to work a lot better. And maybe even at one point, once people are sufficiently educated, enlightened, and oriented, even be able to do something that Saul Kent has been interested in doing, which is to get the political authorities to agree to allow cryonics to begin before the pronouncement of legal death. Animals have a much better time with cryonics than people. Because
or you could just commit suicide at an Alcor facility.
Then you get autopsied or thrown in jail or something.
Ralph, for the last word on cryonics and this session.
Oh, yeah. So, yeah, I'm in entire agreement that that would be an excellent thing to do, and obviously talk with Greg if you have interest in providing support for that. Also, cryonics, I think the idea of gaining greater acceptance for it is very important, and obviously one of the things would be one of the things we discussed this afternoon, which was the intermediate temperature storage. Obviously, there's an area where if people want to step forward, that is a well-defined technical issue, and if people step forward and say, yes, I want this and I'm willing to support it, then I would certainly strive to make that happen. So I think that would be something that would be very interesting. But I think basically greater acceptance for cryonics is something which is critical for a variety of reasons.
We have to come to an end now. We've run out of time. I would like to thank all of our participants very much. I'd also like to thank our amanuensis, Kevin Parrott over there. However, Kevin, I can't let you go without saying I want this written up tonight, and I want in typed form now, not your lovely handwriting, and a copy available for everyone for tomorrow's session.
It'll be PDF'd in David's mailbox, and he can actually forward it to everybody.
Outstanding. You have a procedural issue, Steve?
I wanted to add a new category that has been left out of the discussion on scientific interventions. If I might, just 1 minute.
I'll give you literally 1 minute.
There are at least 5 different clocks that we know about in the body. At the cellular level, the PER and TIM genes that are antagonistic for the diurnal cycle, the circadian rhythm in the brain for pineal gland and melatonin, the monthly cycle of women with FSH and LH. But the one that I'm interested in is the annual clock, the one that is maybe doesn't even exist, I don't know, is somewhere in the hypothalamus that has to do with the onset of puberty. If we could figure out how to manipulate that, we might be able, not that I'm interested in puberty per se, but I'm interested in both puberty and the opposite of that, which in women is called menopause and men andropause, to see if we could stretch it or extend it in some way.
Gene, I thought you were talking about curing the disease, which is teenagers. Thank you very much, ladies and gentlemen.
We finished for today. Is today finished?